and what I'll do is I'll describe several cuts that I apply to the data to remove junky events from the analysis, so I can get the best directionality and discrimination measurement. The first cut is this that I apply to the data. Again, I'm going to show all the results of the cuts in this ln of eta versus energy parameter space. And the first cut is a saturation cut, and so I reject events that saturate the oscilloscope, and you see here where it saturates the oscilloscope. So I throw all of those events away, and they're these red events here, and so the black events are the ones that remain and make it to the next cut, which is this rise time cut. So this rise time is the time difference between the 10% of the peak voltage to the 25% of the peak voltage. So I define this region and I calculate the time in microseconds between there. And if that is less than 5 microseconds, I throw the event out. And the reason is because these events have a fast rise time, a non-physically fast rise time. And so they're like sparks or microsparks or not real events in our experiment, in our detector. So I throw those ones out. And then the next cut is this other peak cut, where I reject events that have a like duplicate or more than one event inside the time window, either preceding the event or trailing the event. And that's this, I call it as other peak cut. And again, the black events are the events that pass this cut, the red events fail it. And the next cut I have is this ln of eta cut, where the blue dashed line again defines the nuclear recoil, the separation, and so these black events are what I'm defining to be the nuclear recoil band, and so I apply that, and so it's this black distribution of events that I'll be focusing on to measure the directionality, the discrimination. I'll be focusing on them. And the last cut I apply is this fiducialization cut, where I make sure that the events were correctly fiducialized inside my experiment. And as you notice, it's greatly reduced the number, the statistics, the number of events that I had inside this parameter space. And the reason, I'll get more into it, but the reason is that it's the low efficiency for fiducializing with SF6. Because I have low signal to noise. I'll point it out, but I just want to mention that this cut removes a lot of events, and here's my my results. So this is the range versus energy, and for the discrimination measurement, you see that here's the electronic recoil band here, and here's where I define the nuclear recoils. And you see I have an energy down to, or a separation between these bands down to around 50 kVE. So this is my discrimination. And so next I measure or I'll talk about the directionality. So, and again, the directionality I measure in terms of the skewness difference, gem skewness minus the gem side minus the cathode side skewness. And I take the data and I plot it in terms of energy bin, so these horizontal bars define the energy bin at each point, and then I calculate this difference. And you see that as the energy increases, the directionality increases as well. And but I want to point out that in this lowest energy bin here, I'm measuring directionality. It's positive, so I'm measuring directionality, and so I can say that I have directionality down to 50 kVE. Yes?
I hate to stop you, but so you're reading out ions on the gem, but what are you reading out on the cathode?
I'm not reading anything out on the cathode.
Then what are you subtracting?
I'm subtracting the skewness, the distribution of the skewnesses that I measure with, so maybe the nomenclature that I use is slightly confusing, but cathode refers to the DD generator, the experiment with the DD generator on the cathode side, sending neutrons through the detector that way. Okay. And then gem is the opposite.
I see.
So, I tried.
Sorry.
All right. Okay, so there's, but as I mentioned, SF6 has this poor fiducialization efficiency. So here's that same signal, SF5 minus, and you see it's this really small blip here, and in fact it's only 2.5% SF5 minus, 2.5% of the total charge of the event. And since it's so low, you see the fluctuations I have in my signal, I can misidentify something else inside the event as SF5 minus, which throws off the fiducialization and is an issue. So ideally, we'd like to be able to enhance this SF5 minus peak so we can more reliably fiducialize our experiment. So that is what I'm going to talk about now. So we started searching for that, a way to enhance that fiducialization. And in order to describe like how we thought we would do that, I want to talk about the negative ion behavior in SF6. So the first step that happens is the particle leaves behind trail of ionization, and that's this electron here, and it is captured by the SF6. And the result of that capture is this SF6 minus star. So we have this negative SF6 minus in this excited energy state. And so it needs to lose this excited energy, and it does it through three different channels. The first one is this auto detachment where the electron is re-emitted. The second one is this collisional stabilization where it collides with a neutral SF6 molecule in the gas, and it loses that energy, and then you have this SF6 minus, which is the primary negative ion, the primary signal. And then the final one is this auto dissociation, where the SF6 minus star breaks up and forms SF5 minus plus fluorine. So what we want to do is we want to enhance this signal, which right now is 2.5%, relative to this one here. And so the way we wanted to do that was we wanted to increase the capture length of this electron. So essentially, if we increase the distance over which the electron is traveling inside the detector, it's accelerating as it's moving. If we increase that distance, it's going to be captured at a higher energy. And so this SF6 minus is going to be at a higher energy state, and that should cause this reaction to be enhanced relative to this one. So that was our idea, and what we did is we took this mixture here, CF4SF6, with SF6 in low concentrations to increase the capture length. We diluted SF6 with CF4, and we chose CF4 because CF4 is not electronegative, and also because for two other reasons is that it has fluorine, and fluorine is good also for the dark matter. That's the target, and we also have a lot of experience with CF4 as well. So that's what we did, and this was what happened. Not at all what we were expecting. We were very surprised to see this, and I was very excited. So this is a signal where I've done that mixture, and this species showed up here, this new species, and this was very unexpected. And so this first signal, this first negative ion peak here, is the SF5 minus peak we were expecting. Here's or SF6 minus. Here's the SF5 minus, but this one we were not expecting. This peak here, and so I'm going to call it CF3 minus because that's what I think it is, and I'll motivate why. I'll give a model for why I think it's CF3 minus. But this was pretty exciting. So I did a bunch of experiments trying to understand what this was, and the way I got that signal I just showed is this here. So I use a laser to send a beam of photons that are impingent on the cathode, and that causes photoelectrons to be ejected from the same location on the cathode, and so those electrons are then captured, and then those negative ions drift the full length of the detector to the readout. And the reason to do this is then the events that I read out, the signals, they're all identical. So I can co-add them, and I can improve my signal to noise, that like noise issue that I was having. This helps that issue. So these are the signals that I'll be talking about in this method for the next several slides.
So Randy, you see what you think is CF3 negative.
Yes.
Why do we not see it in drift? Because it uses CF4.
Well, because there's no SF6. So I'll describe my
So it's
model.
only because-
My
okay.
model, it's crucial that there's SF6.
Okay.
Yes, and I mean, people have been studying CF4,
Right.
and to my knowledge, nobody has seen this before. So I'll describe why.
Okay.
I'll get to the motivation. That actually might be my next slide. No, it's not. Okay. So before I talk about that motivation for why I think it's CF3 minus, I did a bunch of different experiments, and to see how this species is affected by different parameters. So here I have a low drift field, and here I have a high drift field, and you see that with a low drift field, this new species is really low. But and when I raise the drift field, it's huge. It's suddenly the dominant species, the dominant negative ion. And so just by tuning the drift field, I can pick this negative ion species to be what I want. So that was pretty exciting when we saw this. And then I also looked at how the negative ion species behaves when I change the SF6 pressure. So here, the concentration of SF6 is really low. And you see the negative ion, the new negative ion is huge. It's really large. But then as I add SF6, it decreases. Its production goes down. So what this means is I have two knobs now to adjust this species to what we might want it to be. I can change the drift field inside my detector. I have that knob, and then I can also change the gas mixture and increase or decrease the amount of SF6 that I add. So this was really exciting, and now I'll talk about why I think this negative ion is CF3 minus. And so I did a bunch of experiments, and sort of in my free time, I kept scratching my head and wondering, like, what could this be? And Dinesh kept telling me to ignore it and move on, but I kept thinking about it, and this is the model that I came up with from reading the literature. So this is a reaction coordinate. An abstract thing describing the progression of a reaction. So from this, the start here to the end here. And so I want to point out that the start of it is with this SF6 minus star, where you have this excited SF6 negative ion. And so it starts here, and it has this excited energy, this vibrational energy, which I'm going to call E nu. And it encounters a neutral CF4 molecule, and it collides with one. And as it does that, this is the internal energy. As it does that, it moves from 1 to 2, and they start to move closer together. There's this van der Waals attraction between the molecules, and there's this dip here. But in order for the reaction to progress forward, it has to overcome this energy barrier, which it can do by giving up the SF6 minus star can give up this E nu. If it's large enough, it can overcome this barrier. And then now the molecules are in this complex here, where the electron has been transferred to the CF4 side of the complex. And then if that happens, the molecules then begin to drift apart from each other, and then you have neutral SF6 and then CF4 minus. But as I mentioned, or I need to mention that CF4 minus it doesn't want to have an extra electron. It has no stable negative ion state. Unlike SF6 minus, there's nothing like that for CF4. So it auto-dissociates. It breaks up and forms this CF3 minus plus fluorine. So this is why it occurs in SF6 and not in the drift experiment. And then here's the CF3 minus. And so this model that I came up with, it makes several predictions, which is cool. And so it predicts that as you lower the SF6 concentration or you increase the drift field, both of those things will increase the capture length. And so the electron is captured at a higher energy, which increases the energy of this SF6 minus star and this E nu, which means you'll have more reactions that go all the way across, because this E nu is larger. And so that means that you'll produce more CF3 minus, you'll also produce more SF5 minus, and that at the expense of SF6 minus. So it makes this prediction, and I'll show how this is consistent with the measurements that I have. So now I'm going to describe a bunch of measurements where I I tried to characterize this new species. And so here I show the relative amplitude of the species versus the concentration of SF6. So I add more SF6 into my mixture, and I see that as I do that, the CF3 minus, the new species, decreases the amplitude, and similarly the relative charge of the CF3 peak also decreases as you add SF6 into the mixture, and then you see that the SF6 minus increases as you do that. Okay. So the next I show for two different mixtures, I show that as you the effect of the electric field now. So I increase the electric field from a lower value to a higher value, and you see the CF3 minus peak steadily increasing as you increase the drift field. For both of these cases, you see that happening. So you see that if I pick the drift field or the SF6 concentration to be what I want, I can pick what I want the CF3 amplitude and like charge to be.